All right, so here's what we have left between now and Christmas. So we've got 3 days here, next week, next Friday, a week from Friday, that's the day before Thanksgiving break. That's always what I call Africa Day, and we'll talk about my time in the Peace Corps. So there will be no physics done on that last Friday. We'll talk about that. We'll cook, we'll get philosophical, we'll talk about the world.
Cook.
I'll make my famous ranch eggs. We'll talk. So, what's it?
So excited.
Okay.
And I cannot explain.
Luke's a fan.
So excited.
So then, after that, we've got 3 weeks leading up to Christmas. We need to get through gas laws, the physics version of gas laws, not the chemistry version. Thermodynamics, fluids, buoyancy. Got some labs to do with that. And then, and I don't know how this is going to play out yet, but we've got a 2-day lab final and a written final. But I don't know if we're going to have like the same kind of final schedule like May South has, which I think is an abomination, but they didn't ask me.
It's the best thing ever.
No, it's not. It's horrible.
It is.
No, it's not. So they still don't know how that's going to look quite yet. Okay, but we'll talk about that. So what we need to do today is talk about work. Now, work itself is a simple equation. Work equals force times distance, okay? Which in and of itself seems simple. But work is the most complicated simple equation that exists in all of physics, okay? I'm just telling you, it looks simple, oh, it's not. Now, but let's talk about what you have to do work. There's 2 criteria. A force has to be applied, and there has to be displacement in the direction of that force. Okay, so you have to have 2 criteria. There's force, and there has to be movement in the direction of that force. So, start with this idea. If I just hold up this block, am I exerting a force?
Yes.
Yes. But I'm not doing any work. Why?
There's no
It's not
displacement.
It's not moving in the direction of the force, right? Now, if I lift it up, I do work. Now, the other thing you'll see about work is that work can be positive or negative. So the short version of whether work is positive or negative, if it's in the direction of motion or making something go faster, it's positive work. If it's in the opposite direction of motion or making it go slower, it's negative work. And there's really no mathematical basis for that. It's more of a bookkeeping type thing. So, here's your 2 criteria. There has to be a force, and there has to be movement in the direction of that force. So, let's say that I want to calculate how much force it takes to pull this block. So, I'm just using a string because it's going to make it a little bit simpler. So, I'm going to take the string, hook that up to the block. There we go. So I'll turn on the Newton scale, miracle of modern electronics. Turn on. There we go. So I hook this up and I pull it along, and it takes about 0.80 newtons. So when you look at this block, you got gravity acting on the block. I've got normal force acting on the block. I've got my force applied, and I've got my force friction. So if the applied force that I apply is 0.8 newtons, and let's make it simple, and let's say that I pull it for 1 meter, then I would do 0.80 Newton meters of work. Now, That's one option for work. You can put Newton meters. That's smash mouth physics is Newton meters. The other option is that Newton meters and work, because it's very much related to energy, is that you could put a capital case J, uppercase J, which stands for joules. Okay, now this was named after Prescott Joule. Prescott Joule was very popular in high school because his family owned a brewery in England. It's like, oh, let's go party at Prescott's. So, if you look at an overarching theme that connects all branches of science, astronomy, biology, chemistry, it doesn't make any difference. Energy is that overarching theme, okay? And all forms of energy, no matter which class you're in, are generally measured in joules. You can get into weird stuff like in chemistry, we kind of talk about liter atmospheres as a no, stop, it's wrong. Okay, you can do that, but generally speaking, in all rational measures of science, energy is measured in joules. So the reason that works, and the reason that they named it after him, is because he was the first one to find like the mechanical equivalent between mechanical energy and thermal energy. So what he did is he took a very, very, very well insulated container of water, and he had a rod that went through it and had like baffles that could spin. And then he wrapped a weight around the end of it, tied that to a pulley, and he dropped the pulley. So when the pulley fell, that would make the baffles inside of their spin. And as they spun, he would see a small change in the thermal energy of the water. He said, oh, great, these things are related. Which intuitively makes sense, because if you have like two containers, both of them contain the exact same amount of ice. One, I'm just going to sit here. The other one, I'm going to put on a shaking device. Okay? So one is just sitting there. Other one is going to vibrate. Which one's going to melt faster? Chuck.
The one that vibrates.
Why?
More energy.
Yeah, there's more thermal energy, there's more collisions. Okay? So temperature is basically the speedometer of the atomic world. Okay? Higher the temperature is, the faster the particles are moving, the more kinetic energy that they're going to have. So, I don't care. You can use Newton meters, you can use joules. I care not. Pick one. Okay? Doesn't make any difference. So, in this case, I'm going to call that a positive value. Okay, great. 0.80 Newton meters, 0.80 joules, whatever it is. We could draw that on a graph, and we could say, hey, we exerted 0.80 newtons over a distance of 1 meter. So, Andrew, what does the area underneath a force distance graph give you?
The work.
Work. Because it's Newton meters, it's joule. Boom, there you go. Now, if it's a force time graph, Scooter, what does the area underneath the force time graph give you?
Impulse changing.
Change in momentum. Okay? Now, Andrew, stop that camera. Let's go to the back of the room.